Now let's consider the following public good game. In this game, each player decides how much he or she contributes to produce a public good, which benefits everyone involved in the game. The level of contribution is denoted by AI, which costs C times AI units to player I, where C is a positive constant. The payoff that player I gets from contributing AI is a function of the total amount of contributions made by all players and the cost of making contribution incurred by player I. In order to obtain the best response of player I in this game, we take the first order condition with respect to the contribution amount AI and set it equal to 0. Then we express AI as a function of the opponent's contribution amount to get the best response function of player I. We now call best response correspondence as the best response function because the best response of player I is a singleton. The summation sign J not equal to I here means sum of all contribution amount, excluding player I's contribution. Now we have n players in this game. And so this means that we have a system of n equations with n unknowns where the unknowns are A1, A2, A3, and so on. To solve for the equilibrium contribution amount, we use some trick. The trick here is to obtain the total contribution amount first, and then divide the total contribution amount by the number of players n to get the individual contribution amount. To do this, we sum across all first-order conditions. The resulting sum of first-order conditions is just a function of sum of all contribution amount, which gives the equilibrium total contribution amount as the 100 times n divided by C times n plus 1. Here, we try to obtain a symmetric Nash equilibrium where all the players take exactly the same strategy. And so we simply divide the total contribution amount by the number of players n to get the symmetric Nash equilibrium strategy of player I. We find that each player contributes 100 over C times n plus 1 units of his private goods in a symmetric Nash equilibrium. Note here that the contribution amount in a symmetric Nash equilibrium is not Pareto efficient, in the sense that every player can be better off by increasing their contribution amount to 50 over C. To see this, suppose that every player contributes 50 over C. Plugging this contribution amount into the payoff of player I, you will find that player I gets indeed larger payoff than the payoff under the symmetric Nash equilibrium contribution amount. The intuition here is straightforward. Every player wants to free ride on other players' contribution because making contribution is costly while you do not have to pay anything if other players make contributions. Another interesting prediction of this public good game is that player I's contribution amount is decreasing in the number of players n. And so the more people involved, the smaller contribution is made by each player. Let's consider Cournot duopoly game. There are two firms playing the game. The strategy of firm I is the output of homogeneous product Qi, which is a positive real number since you cannot produce a negative quantity. The payoff of firm I is given by the profit generated by selling output Qi. which is the difference between the total revenue P times QI minus the total production cost C times QI. Here, P is the price of the homogeneous product, and C is a constant marginal cost of production. The inverse demand curve is assumed to be given by the linear function A minus B times total output. A and B are both positive constants. Plugging this inverse demand function into Firm I's profit function gives Firm I's profit as a function of rivals' output. We are going to derive all pure strategy Nash equilibria of this game. Following exactly the same step as the case of public good game, we take first order necessary condition to derive the best response function of Firm I. The best response function here takes into account the fact that output cannot be negative. We can draw a graph of the two best response functions and find the intersection which gives the Nash equilibrium of the game. Let me summarize what we have done so far. To find Nash equilibria, first, we eliminate strictly dominated strategies. And this simplifies the problem of finding Nash equilibria a lot. The second, if each player has a best response correspondence, derive all Nash equilibria by obtaining the strategy profile where every player best responds to each other. Lastly, we find all the intersections of best response correspondences to obtain all the Nash equilibria.